Hello everyone. Today we are going to learn about Merkle trees. Sunny is going to teach me and Vivek what Merkle trees are and how and where we can use them.
Thanks and hello everyone. So today we'll talk about another data structure, which is Merkle tree. So Merkle tree is a data structure which is also called a hash tree. What do we mean by hash tree? Is basically it's a tree created using hash of data. So generally when we talk about other data structure side, we are storing actual data in the tree, but in Merkle tree we store only hash. Now, how these hashes are being used to solve what kind of problems? So let's uh, go deeper into that. So, so let's think of the problem statement that you have a very large file which you want to send, let's say over a untrusted network, or let's say if you share with someone. So how do you verify the authenticity of the transferred file? So let's say I transfer file from my uh, laptop to, let's say, Vivek's computer. So how do I verify if the file that Vivek has received is same and there's no change in that, or let's say there's no data corruption due to the network? So how do we verify that? So one way is your name way will be that I compare block by block, or let's say complete file,
Mhm.
and then basically that will give me the output that whether if some part of the data is corrupted, if I get some mismatch. But that will be very compute intensive and requires very high network data transfers. So to overcome that, another optimization we can do is, let's say I compute a hash using one algorithm on my computer, and same thing Vivek also does at his computer, that computes the hash of the file using the same algorithm, and then we can compare the hashes. So and that way I don't need to do like transfer the whole file, but I can compare the hashes. So only the hash will be needed to be transferred from one computer to another computer to verify the correctness of the file. But now let's say if we
Okay.
are able to find that the file are not matching, then how do I fix it? Like from where the corruption started, I don't know. So to efficiently detect it, it uses a tree kind of structure so that I can fastly, if I'm using just a, let's say if I divide one GP file into, let's say, blocks of 1 MB each, and if I'm
Mm.
doing a linear comparison of each 1 MB block, that if I'm comparing hashes of each MB block, then it will take me 1,000 iterations to compare it. But if I'm using something like Merkle tree, I will be able to do it much faster. So you'll see how fast as compared to the normal linear approach. But the overall goal is to do these kind of operations very fast and to be able to detect the corrupted portion, and to be able to fix it in the faster time. So that's the overall, you can say, use case that is there. Now let's see how we do that using Merkle tree. So Merkle tree is a simple data structure where what it says is every leaf node sorry, corresponds to hash of your you can say block data. So you divide your data into blocks, and then
Mm.
your leaf node is a hash of basically your block of data, and every non-leaf node is your basically hash of its childs.
Children. Children. Okay. Children.
So now, for if there are multiple childs, right? Like for a binary Merkle tree, it will be like two nodes. So now you can
Mm.
take hashes of both, and you can say concatenate using a plus. You can just concatenate and take a hash. So that's up to you, like how you want to design that algorithm. You want to concatenate, you want to append some character, and then do it, let's say underscore, right? So that is up to you. But you will follow some semantic, and then you will finally have a root which will represent a final hash, you can say. So this is your Merkle tree. So that's the computation part, how you compute it. And then once you have this tree, the only thing that you need to do is compare the root of the, let's say, two places where the data is residing, and compare if the root is matching, that means your data is correct. If root is not matching, that means there's a mismatch. So that's the
Can you
whole.
show how the tree will look like as an example?
Let's look at the tree. Let's try to create a tree. So basically, let's say this is your root. Now create copies of it. So we'll create a binary. We basically you can also create a n-ary kind of structure. But for simplicity, let's create just a binary. So let's look at this simple tree structure. So what we call it, let's say this is our block 1 of data. This is our block 2. This is block 3. This is block 4. So what we'll do is compute the hash of this block of data using any standard algorithm. You can use SHA-1, SHA-2, SHA-56, MD5, right? I think probably it will be good if you can talk about the properties of the hash algorithms that can be used for this problem statement later. But let's say we compute the hash. Now this will give us hash H1, H2, H3, H4. Now what it says is you for computing hash of this node, we'll have H12 and this will be H34. And this will be your hash root. We can call it H. Cool. So this is how your overall Merkle tree look like. So you have your base hash, basically your blocks of data. Rather than storing the actual data, we compute the hash of this data, B1, B2, B3, B4, corresponds to H1, H2, H3, H4, and now H1.
So in case a block is changed, then the whole chain has to be updated.
Correct. So if you look at, let's also talk about all the operations that are required. So first is creating this tree will take how much time. So if you have n number of data points, so total n plus n by 2 plus this, so total 2n operations will be required, which will be order of n, if you do the math. So you can create a tree in the n number of operations. Second comes out as, I think.
Wait. N plus n by 2 plus n by 4, that is a quadratic, that is n square.
No. It is summation, right?
Acha, take it, half.
It will be 2n.
Yeah.
So update in the tree, like Vivek was saying, right? So let's say if the block 3 of the data changes, then I need to only compute these hashes again up to the length of the tree. So it will be order of log n. So third is, let's say you are able to you're transferring the file. Let's say you had a data mismatch. So now if your mismatch is only at a particular place of the data, let's say only one block was changed, right? In that case, like you will compare the root hash, it will not match. Then you'll come down. So let's say B3 was corrupted. So then this will basically not match. This will match. So you don't need to go in this side. You only need to go H34 side, and then you can basically come to a particular leaf node. So in worst case, it can be like if your all blocks are corrupted, it could be ON, order of n. But if a particular block is changing, or like in general cases when where part of the file is corrupted, you should be able to do it in log n.
Okay.
You can say best case or something.
This is this is complexity for searching, right?
Yeah, this is for basically when you are okay, let's name it.
So it's not exactly searching.
Finding corruption or something like that, matching kind of.
In case of,
or you can say verification. data verification.
Basically finding the corruption.
In which case it just a quick thing. If we have to find the corruption, then it will wouldn't it always be login?
No, it depends on how many blocks are corrupted.
If all the blocks are corrupted, then it will...
Effectively you are traversing all the nodes.
Wouldn't it be n log n?
No. The total number of nodes in a binary tree will be, if you have n leaves, it will be 2n.
2n minus 1.
Okay, got it.
2n minus 1.
Okay.
So basically you will end up going to all nodes, which is your order of n, right? So I think these are your typical operations that you will be performing on your Merkle tree. So creating will take O(n) time, updating will take log(n) time, verification takes log(n), but correction takes actually O(n).
Correction will take...
Actually, we can split
best case.
parts.
Best case.
Best case log(n), worst case O(n). Verification is verification mein worst case is actually verification is your order of 1 only, right?
You can just check the node which
Yeah, you can just check the node and say that whether it is matching or not. If it is not matching, then you can say that.
Yes.
Correct.
So it depends. When you say verification, you just want to check whether both the trees match or not.
Correct. If something is connected or not.
If you want to find which node is not matching,
then it will take time.
Then it will be log n or worst case n.
Cool. So now we know what is Merkle tree. So let's look at what are the use cases of Merkle tree. So first is Git. So we all have used Git. So Git actually uses Merkle tree to compute what has changed, what has not changed, and when you commit, it will use Merkle trees in its local to detect those changes. Second use case is in NoSQL databases. So NoSQL databases have this concept of multiple replicas which are being maintained automatically, right? So how do you know if a replica is corrupted or not? So they do compute the Merkle trees of the hash data, and then by that Merkle trees, they will know that if some replica is corrupted or not. If something is corrupted, then you can also find which block is corrupted, and then you can fix that data point. Third is in your blockchains. So let's say as the transactions are happening, so to verify the correctness of the blockchain, this concept is used where for every transaction you add the hash of the transaction and then verify it.
In case of blockchain, it is not a tree, it is just Merkle chain then.
No, so it will be tree. Overall it's a tree, but you have a list of transactions, right? So you will not compute per transaction probably. You will do like in a list of transactions will be put inside a one block, and you verify that you have the hash of that particular block. Similarly, as the transactions are happening, more blocks are getting added, and your overall root of the whole blockchain will be your whole total hash.
Okay. But
in blockchain, each transaction block as a leaf.
Yeah, each you can say block of the transaction is a leaf. Yeah. So the last example basically that we know of is any system torrent system, right? Where you download the torrent file, and then how basically these files are being transferred. So the torrent file actually contains the data about your hashes, and you download it from an authentic source. So that first thing is you need to know the authentic source of using which you know the root hash. Once this comes from an authentic source, verifying other data points is little easy. So That's why we download torrent file from an authentic source, and then basically the P2P transfer can happen. If some like P2P, peer-to-peer, in one transfer we get some corrupted data, then it can verify and fix it and download it from some other source.
Okay.
Cool. So now we know the use cases. Do we have any limitations of this? So from security point of view, there could be one issue. Like if you look at the security aspects. So how do I like corrupt this? Let's say if I'm a person who wants to break this thing, right? Let's say in the torrent example, can I mess up with the hashes and basically be able to attack this? Let's say put some corrupted data into the system. So basically, rather than B3 and B4 being present in my system, what if I put the hash of H3 and H4 and create that as a file? Because B3 gives H3, B4 gives H4. So the problem is basically you don't know what is the height of this tree, right? So what if I say that I create another thing here and I represent this as the final data here, where I create this as a leaf node having the data of H3 underscore H4. How do I detect that whether this is a leaf node or this is a non-leaf node? So these are some kind of attacks that are possible, but to overcome that, there are other implementations basically where rather than just using the data, you append some special things. Like if it is a non-leaf node, you append like 0x01 kind of thing. But if it is a leaf node, you append 0x00. So that way you will be able to ensure that hashes will match only if it's a leaf or non-leaf. So because that's the only detection you want to do.
So in this case, your H3 underscore H4 is basically some content which will also map to map to H34 as the final hash.
Yeah.
That basically means it's a collision hash. Hash collision is the problem over here.
Right. But okay, let's go into more details. What kind of hash functions we need here? First thing is deterministic. What we mean by deterministic is that for a given value, it should hash to the same value deterministically every time.
Okay.
Second is it should be collision free, right? Like
collision resistance or free.
or basically it should have minimum like there, right? Minimum collisions. So given two different values x and x dash, hx should not be hx dash. Okay. Third is basically pre-image attacks, which are your brute force attacks, right? That given a value, hash value y, I should not be able to guess what is the x for this. That is pre-image or brute force attacks.
So pre-image resistant or collision resistant?
Yeah. So computationally, we should be efficient because we have to compute hash of a large data, right? So it should be efficient to calculate the hash of the data. So today we learned about Merkle tree, which is a hash tree, and this hash tree is created using this following rules, where leaf nodes contains your hash of the block, your actual data, and non-leaf nodes are hash of its childs, and then root is your hash of basically, if you look at the hash of the root, that effectively will look like hash of your total all the data. And just by comparing the root data, you will be able to find whether there's any change has happened in the data or not, and if there are two copies of the data, whether those copies match or not. And these are the different use cases where it is used. And for creating a tree, it will take n time, O(n) time, and updating will take log n time, because we will just need to follow the path till root to update the tree. And data verification, that whether the two tree matches or not, it's a O(1). And once we know that it is not matching, let's say, and correction of data with respect to updating the data will take, in best case, we should be able to do it in O(n) if only one block is corrupted. But if multiple are corrected, then for every such block, we need to go till the leaf, and then total it will take O(n). But in most cases, you should be able to do it in 1 or 2 blocks if your part of the data is corrupted. And by picking a hash function with these properties, we should be able to simply build this hash tree, Merkle tree, and use it in production.
Okay, great. Thank you, Sunny. This gives us a really good overview of Merkle trees and where it can be used. Well, thanks everyone. We'll see you in the next video.